I'm going to show that I didn't always want to be a scientist. In fact, I'm not sure I ever wanted to be a scientist. And as a kid, I wanted to be Superman. And I thought I'd show you some proof of this here. Flying was a bit difficult, so I had to do other things. And I played a lot of tennis. I actually played for University of Sussex when they didn't have any students to play tennis. I did gymnastics at school. And I also acted in a play, Henry V. And the reason for showing you this is that education in chemistry is not just education in chemistry, it's other things as well. I'm the handsome guy on the right, just in case you didn't recognize me. And I usually tell teachers, you must not let any of your students become actors, because the guy in front became an actor, and he's now 5,000 years old. And I'm a lot younger than he is, right? Ian and I were in the same year at school, a fantastic actor at school. And in fact, he came out to Tallahassee, worked with the drama school there, stayed with us for a few days, and he's been a friend. And he's presently filming The Hobbit in New Zealand. The other thing that's probably more important than science is graphics for me, because when I was a kid at school, I used to do a lot of drawing, and I got extra lessons from the art teacher and from the chemistry teacher. These two people realized that I somehow had some abilities, and they decided that they should sort of promote it. And I think one aspect of a teacher is, I think perhaps the most important one, is to uncap the creative potential of every kid in the class. That's extremely difficult, you know, because in general, maybe only 5 or 10% of the kids are really interested in your subject. But these are some of the things I did at university. I was art editor. Could you just have the lights down a bit? Okay, because I don't want the lights down. Okay, I don't want it. Well, there you go. There's something a bit odd. Anyway, because otherwise you can't see the. Okay, that's fine. So I was art editor for the Sheffield University magazine, and I think that's important for me as well, because, you know, all this thing about in the future universities going to be on the internet. For me, at least 50%, maybe 80% of life at university was meeting other people in other disciplines, not just in chemistry. And I have lifelong friends who were editor of the newspapers, and they were dentists and other things of this nature. So those are the sorts of things. I got into an annual of graphic design for this one. You notice that the University of Sussex is the only chemistry department that lights its Bunsen burners. Of course, we don't have too many Bunsen burners at the moment. But in fact, these are some of the things. This is my book. And my first award was not for science. It was for this design. And it got me the Sunday Times award here. And I used to look like this. Now, I think you should point out as teachers that the young kids are young and beautiful now, but they're going to look old and decrepit like me one day. So they better get thinking about these things. This was actually one of the technicians here. And he had his own rock group, and not quite sure what that is, but there, go on. So these are the sorts of things. This is my wife, Margaret, and so these are a lot of these things that I used to do. I now do logos, and this is the Kroto Research Institute in Sheffield. Designed their logo, the Kroto Research Campus in Sheffield. And I do also workshops with small children, and this is a buckyball workshop on C60, hands-on, down in Australia, which was actually broadcast across the whole of Australia to 2,000 kids in about 30 schools. I'm trying to sell it to the Australian football team, but they're not that good, actually. They're much better at cricket. So these are some of the things. And, I redesigned the Japanese flag, actually. It's just shown here. Designed this stamp for the UK. And this is my recent one. I'm now in the USA, and they don't understand the Constitution or Jefferson and Madison attitudes to these things. But I guess the final straw was when I only got good for my frog, and I used to get very good for my maths, okay? So I ended up in science. And I also, this is a real 60s picture. You wouldn't be invited to a party unless you could play at least 2 chords on a guitar. And this is Dave Santry, a friend of ours, and Mark's in the middle, looking at very much 60s. The other thing is I had Meccano. How many of you have Meccano? Okay, that's quite impressive, because I had this and played with this, and I thought I'd show you an advertisement from those days. Meccano boys, and of course today we've got to add girls, are keen, ambitious, and inventive. No boy or girl who follows the Meccano hobby can be a bad boy or bad girl. And we also had, at the BA meeting, we had Meccano workshops and buckyball workshops. And it's fantastic to see kids who are just totally absorbed. And my view is not that they do something that they enjoy, because I don't enjoy hard work any more than anybody else. It's something that absorbs the kids so that the hard work becomes easy, okay? That's what I think we should be doing. And you can see these kids just working away with their hands, putting things together with nuts and bolts. And today, I put things together with electrons, okay? That's what a chemist actually does. The other thing I did as a kid was I used to go through all the travel agents and take all the free brochures. And they were works of art. These are fantastic works of art. And one of my favorites is this. It's a brilliant painting. And so, as a kid, I had this influx of art and graphics. And then I started to collect books. And this is my first book for 2 and 6pence, Ronald Searle's Refugees. Beautiful drawings. Now, I think what epitomizes the problems that we have in science teaching is this. This is taking a photograph, okay, in the old days. How many people remember that? Quite a few of you. It was quite a job to get a photograph, and this is a picture I took of myself when I was 17 through all that particular thing. And I think you really do have to have a lot of incentive, and I did have one. And but today, basically, that's it. Now the kids have lost everything about what's going on. I don't think many of them understand what's going on inside it. I understood everything about the camera. I understood optics. I understood how the exposures work, the reciprocal factors, the F numbers, the depth of focus. I learned some chemistry of putting the whole thing together. I don't have very many photographs, but at least I knew how they were achieved. And I think this epitomizes our problem today, because our kids have got mobile phones and many other things. They have no idea what's going on. That is the biggest change, and one I think the biggest difficulties that we as teachers of science have in getting kids interested, because they can't get inside it. If things go wrong, when they went wrong, the radio went wrong, I fixed it, okay? I made my own radio. I took out the valves of the family radio, that's all we had. When it didn't go, which was every 6 months, put a new valve in, and I learned how it worked. The other thing that interested me was architecture as well. So again, this is a drawing I did when I was about 14 or 15. It turns out that was where the Nobel Prize was awarded in Stockholm. And Le Corbusier's building, this is Frank Lloyd Wright's Falling Water, and one of the buildings in Venice. And I've played around also with some ideas about the Sussex architecture. And this was also an important building, which comes in later in this story, that I was fascinated by Buckminster Fuller's dome at Expo in Montreal. So the point about making it, this part of it is that education in science is not just education in science, it's education generally. The molecule that fascinated me when I was a kid at school was benzene, where you take 2 hydrogen atoms off this. And then I got quantum mechanics, okay. 2 times 3 is equal to 6, 3 times 2 equals 6. But in the quantum world, A times B is not always equal to B times A. And that interested me. And to understand spectroscopy, which turned out to be my subject, and to understand what is going on in space, you do have to, at a root, to understand, understand quantum mechanics. What is going on when a photon, which 90% of your information comes through your eyes, what's going on when a photon hits the back of your eye? And the paper that was most interesting was this one by Van Vleck, which says practically everyone knows that the components of total angular momentum of a molecule relative to x, y, z fixed in space satisfy commutations of this form. Well, when I came on the campus this morning, I asked quite a number of the students. Well, that was Van Vleck, of course. Now, I think what epitomizes science for me is this. Consider the numbers 1, 3, and 5, okay? Now, I can really sort of cap the whole of chemistry in 30 seconds. The Earth orbits the Sun, we use classical mechanics. An electron orbiting a nucleus, we use quantum mechanics. And basically, in the modern world, many of the things that we use really do involve quantum effects. And for a spinning atom, basically, there are various orientations. Okay, there are only certain orientations allowed, okay? So these are some of these. And when the quantum number j is 0, okay, 1, 2, 3, 4, for a given j, there are 2j plus 1 orientations. So j is 0, 2j plus 1 orientation. When j is 1, 3 orientations. And when j is 2, 5 orientations. Hence 1, 3, and 5, okay? So that's interesting because it relates to the most fundamental aspect of quantum mechanics, which relates to basically angular momentum. As, of course, you know in Newton's case, to try to understand the way the Earth moves around the sun. Let's double that set, and double that set. Move this to there and that to there. Double that set, double that set, double. Move this to there and this to there, and what have we got? Chemistry teachers should know. Yes, it's the periodic table. It explains the whole of chemistry, all of life, and all the useful bits of physics. If any. Okay. Well, of course, we chemists always have a chip on our shoulder because physicists, we're the emperors of the universe. Of course they are. Physics is basically science, the way the universe works. But chemistry is that massive part of physics, of science, which relates to our world, room temperature, food, biology, and stuff of this nature. And it's based on the numbers 1, 3, and 5. Fantastic. When I sort of realized that, it was a very strange moment to realize that something so simple could explain so much. Now, when I did a PhD, I was at Sheffield where George Porter was the professor, and I started on flash metalysis, okay? So what is it? It's basically a quartz cell, a spectrograph, a spark trap, a capacitor, UV flash lamp, photocell, delay unit, another spec flash, and then a lamp, and then the quartz cell. Now what happens now, you fill the quartz cell with, in my case, methyl bromide, then you charge up the capacitors, then you fire the spark gap, the capacitors produce a flash, you produce a radical CBR, you send the flash through there whilst the CBR is there, and you get a transient absorption. And this is my first spectrum. And I got this spectrum, and I was sitting looking at it, and my supervisor, Richard Dixon, came in, and then what he did, basically, he actually, before I forget, this, you can also look at kinetics. I've just realized I've changed this particular part of the presentation. So that was what George Porter did. What I did with Richard Dixon at Sheffield was spectroscopy. And I remember looking at this, I got this, my first result, and I was very pleased with it. But he came in and sat down and he took out a magnifying glass and blew this up, and it blew my mind because there was this beautiful rotational structure. It was just the cathartic moment where one could look at that and produce an analysis of this molecule. And that was the start. Now, when I came to Sussex, there was something called the double bond rule, which said basically that second and third row atoms don't bond to carbon. Well, OCS indicates that that's not correct. But with molecular spectroscopy, working here, I started to show that this rule didn't apply. We made all these molecules, but all of them were effectively new. And then working with John Nixon, we started on phosphorus compounds. Now, when a molecule with a dipole moment rotates, I can give it or take in a photon, and that's microwave spectroscopy. And from the rotational motion and rotational frequency, you can get the structure. And with John, we've produced a whole raft of these. In fact, we've produced the first carbon-phosphorus double bonds, and we produced a whole range of carbon-phosphorus triple bonds. There was only one which had been there around 10 years before that. But the molecule that really started this particular talk off were these two at the bottom, which were made with David Walton. And Dave Walton had produced this beautiful method of stringing carbon atoms together. And here's a picture of Dave with me some time ago. And he'd made a chain of 32 carbon atoms. And it was basically a copper-catalyzed coupling reaction. In the presence of copper, basically the oxygen takes out the hydrogens, and you string the carbon atoms together. Okay, so that was the method that Dave had invented. Now, what happened then, basically, is that we synthesized that molecule, and that was done by an undergraduate, Anthony Alexander, on a chemistry by thesis course, okay? And my idea was, what happens when a long carbon chain, in fact, actually, it should just go by itself, actually, does it? Yes, it does go by itself, all right. Forgotten how that one worked. The idea here was, if you have a long carbon chain, and it's vibrating. How does the Bohr correspondence principle apply? How does the quantum picture apply to the classical picture? And I want to stress that that was the start of this project, okay? I want you to think about this, because this is important today when it's very difficult to get research funding, all right? That led to some radio astronomy work because we synthesized the molecule, and Charles Townes, who invented the laser, also made a breakthrough in interstellar chemistry and showed that using a radio telescope, you could detect molecules in interstellar space. And this is the telescope in Canada that I photographed in the middle of summer, as you can tell, in Canada. And this telescope was the one that we used to show that this molecule was in space rotating, giving out photons, and you could detect the frequencies very, very accurately. And we showed that all these molecules were out in space between the stars. And here's a picture when I used to have some hair, and you can see here we were so proud it got into the newspaper, and I thought I'd show you the chemicals were discovered thanks to Canadian work in radio astrology, okay? There you go, but research by the Sussex team. Then an amazing star was detected, which is this one, which was blowing out carbon and the carbon chains. And that led to some thoughts I had that the molecules that we had detected in interstellar space were actually produced in the star and pumped out into space. And in 1984, at Easter time, I met Rick Smalley at Rice University, and he was taking a laser like this and vaporizing these things and producing clusters of metals, silicon, and things of this nature. And I thought, well, as I was watching what he was telling me this, that maybe if we changed it to graphite, we could produce the carbon chains and simulate the conditions in a star like this. That was the simple idea. Just vaporize it and see what happens. And here with Jim Heath, Sean O'Brien, Yuan Liu, we got a fantastic signal on the 4th of September 1985, and this is my printout, and I put C60 plus question mark, C60 huge, C70 also. We were so elated we went to this restaurant, okay, and started sort of ruminating and drawing on the paper what could be going on. I went back to try and get the paper that we'd drawn on, but when we knew what it was, but they'd cleared the table away, but at that time. So what have we done? We'd vaporized graphite, which is basically, as you all know, sheets of hexagonal graphite. And this is the floor of Bob Curl's loo, and I used to sit and contemplate this floor every morning to see what was going on here. But I couldn't work out what was going on. The other thing, in 1967, I had been at Bell Labs in the States, and we had gone back to Montreal, because I spent 2 years in Canada. Went back to Montreal and saw this building. And I had this photograph in a book, and was fascinated by this structure. But there are many things I didn't know about it. Anyway, that was a clue to what might be happening. The other thing is I had made a model for my children many, many years before, and I couldn't quite remember the structure of it, but I knew that it also, as well as having hexagons, had these pentagons on it. And the next night, Rick made the model. He started off with hexagons, and when he put the pentagons, the whole thing magically closed up. It was just a cathartic time when it popped in, and it was right. That had 60 vertices. And then we decided it had to be right. It was a soccer ball. We didn't know it was a soccer ball at first. We had to really be told that what it was. So somehow we'd vaporized carbon and produced a whole load of these balls. Okay, so that was the situation. But we had to have proof. I came back to Sussex and spent time here with Amit Sarkar and Jonathan Hare, who well known. Jonathan's definitely well known around here. And here's John adjusting these electrodes, okay? And one day, on a Monday, he put this red solution on my desk, okay? That was 6th of August, 1990. And we were thinking, I think, you had a mass spectrum, a 720 mass spectrum. We screwed up big time, really big time. Because it was just so impossible to believe. I think you said we should publish that, right? Maybe we should, but I think we've still been late. But anyway, to cut a long story short, that was on the Monday. On the Thursday, I think we tried a mass spectrum. And on the Friday, I got a call from Nature. That's the journal. And they said, would I referee this paper? Friday, 12:05, a fax came in, Black Friday. It was an amazing paper by Kretschmer, Lamb, Fosteropoulos, and Hoffman. And it was solid C60, a new form of carbon. As I read through the paper, a wine red to brown liquid. And John had put this on my phone, and we had a 720 mass signal. And that was it. It was an amazing paper. There were crystals of carbon. Now, I'm sure that if a kid had said, we're going to crystallize carbon from benzene in 1985, no one would have believed it possible. So here I am in the coffee room, and thinking, go for lunch or commit suicide. Now, I don't know what it's like at where you go to school, but at Sussex, there's not a lot of difference between going for lunch and committing suicide. But anyway, but there was one thing in there. There was no NMR. I was reading through the paper. There was no 720 mass signal in that first paper either, in the manuscript anyway, for searching. So we'd been picked to the post, but that is a fantastic paper. The paper by Kretschmer and co. is one of the most beautiful pieces of chemistry. It really is one of the greatest pieces of chemistry of the 20th century. I was the second one. Anyway, the thing was that basically we went for the NMR. Tony Avent called us up, said, you better come down. We've got a fantastic one-line spectrum. So he said, there it is. And it's, wow. So there's only one problem. He said, that's benzene. That's been done. Okay. But if you look here, and that little miserable little line is the first NMR spectrum of C60, because all the carbon-13s are equivalent. And then Roger worked out that you could separate it. I used to work with Jim Hansen, and they sort of worked out how to separate it into C60, magenta, and 70. And so there's the one-line spectrum, and C70 has 5 lines, and we got the second paper. Well, here is the team with Rice University, Bob Curl at the back, Sean O'Brien, Rick Smalley, Jim Heath, and here is Allah, who's here in... He lost a bit of hair. Yeah. But so have I. All right. Anyway, to cut a long story, here's a picture of Don Hoffman. This is an amazing paper. If you get to read it, you should have a look at it. It's a wonderful story. There's a whole load of Fullering chemistry, which I haven't got time to go into. I want to get on to some other aspects. The fantastic thing about science is the internationality. It doesn't matter what country you are, what color you are, what religion you believe in, or whatever. The one thing that we have that is independent of what you would like it to be is the universe, and that's what it is. And here we see some of the group that was involved in it. In fact, this is not really all my group. It's Roger Taylor and Dave Walton is three supervisors of this particular group. Now, let's talk about some issues of the moment, such as genetic engineering, which people think is actually new when it's not. Without any knowledge of DNA, this animal's been made into a chihuahua. And with knowledge of DNA, you can probably do that in one step now. In fact, you can probably make a human being into a chihuahua, especially politicians. I think they already got the brains of a chihuahua, so I think that's the case. But what is interesting is that nanotechnology is basically several definitions, but one, and I think perhaps the most worthwhile and useful one, is atom by atom, molecule by molecule assembly of a complex or functional system. Bottom-up assembly. It's chemistry of the 21st century, more complex chemistry, okay? And by that definition, we are examples of nanotechnology. We've been built up protein by protein, okay, on the basis of a DNA blueprint. And that's a little clue to the future. The chemistry of the future is going to be based on controlled blueprints, assemblers, and stuff of that nature. And basically, what we're doing now is just putting things together and hoping they stick together. Life doesn't do that. It controls that assembly system, and one might ask whether one day it will be possible to basically produce a computer. And what's happened already is that basically the brain has been created protein by protein assembly. Okay? That's the future, and I think obviously if it's been done once, it can be done again. All right? So that's what nanotechnology is, and we're doing a little bit of this. I'm in Florida State now. Florida State, Jeff. All right. Basically, half the people make this mistake. University of Florida is in Gainesville, where they got a lot more alligators. You want to go to Tallahassee, they've only got 1 or 2 in the museum. Okay. And basically, here's an idea. I think these beautiful images of the sort of ferrite core memories are really quite interesting. You pass half the current you need to magnetize one of those down there, the other half down that corner. At the same time, you can magnetize the core. So that's basically something that interested me. And the question is whether one can do it with a metal organic framework system. And we're getting a little bit of in that direction. We haven't got magnetic clusters yet, but we have made two-dimensional arrays of nickel clusters. And the idea is the following, that if we can assemble it, instead of knitting it together by hand, can we do it by chemistry, then we can go in one dimension down by 10 to the minus 7, which is 10 to the 14 in 2 dimensions down from the original ferrite core memories. So that gives you an idea of what is possible. We're nowhere near there, but we're getting slowly the first rung of the ladder. Now, you may think C60 is my favorite compound, but it's not. My favorite compound is this one. It's nitrosoethane. And the reason is that's what it looks like. and what does it look like to you guys? A dog. That's right, it's my dog. Carbon, hydrogen, okay, nitrogen, red nose. I can look at the microwave spectrum, which looks like a mess, but in fact you'll see a triplet there and a triplet over here, and we can disentangle that into the various compounds. It's a beautiful spectrum. But by looking at the spectrum, we can show that the dog shakes its head, all right, and looks at its tail. Not only that, it undergoes internal rotation, basically like this, all right? Now, of course, it's got a red nose because it's been drinking, it's been on the east bar or something. There's 17 bars on this campus. That's another good thing about this place. You don't have to stagger very far to another place to get a drink. But the dog is, if you're a dog and you've been drinking too much, you know what the problem is. And the most important thing is a lamppost. All right. Now, the reason for showing you that is to remember something that really has been not appreciated, and that is that molecules are flexible. All right? The danger of CO2 is its vibrations. It's not CO2, it's the vibrational mode, the dynamics of CO2 which absorbs the infrared, which is basically re-radiated from the ground. And I think that's the future. Basically, this is Max Perutz's hemoglobin. It's the first molecular machine that was recognized. It captures oxygen in your lungs, transports it, holds onto it there, changes its shape where it's needed, and can release it. It's a fantastically sophisticated molecule, much more sophisticated than any molecule that we have developed at the moment. The most amazing molecule of recent years for me is ATP synthase. Now, just look at this molecule. Basically, protons are going onto this wheel and they're neutralizing a negative charge. The wheel is turning. Basically, a rotor inside here is opening and shutting these cases. ADP is going in with P and ATP is coming out. In your body, zillions of these are going on at the moment, creating the ATP, which is what powers your whole biological system. You're driven on electricity. I just wish Faraday could have seen that. I'm sure he would have been absolutely delighted. When I saw this, I thought, I want to start research again and play with these electric motors. Okay. Protons driven in aqueous solution. Fantastic. There are little bacteria which open and shut their cells like an iris. And that one little piece of nanotechnology that we did here before I left was that we showed that some molybdenum sulfide nanotubes acted as shock absorbers. Going to this, perhaps this is the most important part of my talk, because people don't really understand what science is. First of all, there are pros and cons, okay? There are negative things that happen, but I think the worst thing is the fact that we send young people to go and kill each other with our modern technologies. But by and large, I think, of course, there's Bhopal, thalidomide, and things of this nature, which are terrible tragedies. But I think by and large, people will say modern life is really been improved by the fact that we have all these. And if we didn't have them, if we'd said, let's not do any chemistry in 1900, as people are saying about nanotechnology today, then basically all these things would disappear. And physicists, biologists, engineers can make similar claims. Basically, scientists work together. All right. Well, let's see what we have done. Let's look at what it was like to have an amputation without an anesthetic. Take a good look at it, and our students should have a good look at it. Women had mastectomies without anesthetics, okay? So this is very recent. There can be no more humanitarian contribution than from chemistry than anesthetics, all right? That's only one. Penicillin, we know some of the stories, but let's just look. This is a very simple molecule compared to hemoglobin or ATP synthase, okay? We've not even started to produce the drugs with the sophistication of the enemy, all right? We need to get the enemy on our side. You don't need to pray. This really works, okay? Blood poisoning in 1942. This little girl would have died a year earlier. There are kids in parts of the world dying today because they don't have access, maybe in 1/3 of the world, certainly a quarter of it. In 3 weeks, she was cured by penicillin. I have a colleague who owes the fact that he has a right arm to the fact that penicillin was available to him, okay? It's on my Vega site, and here is one of the heroes of that story, Norman Heatley. The future, as you know, bacteria are evolving with an immunity to antibiotics. We need some fantastic young kids to solve these sorts of problems, okay? But who are the scientists? There's a misunderstanding. This is a typical example that the kids are subjected to on television, you name it. Here it is, and can we shake off that mad media image? And the problem is this guy, because people think that this is a great scientist when actually he's an imposter. He didn't actually do all that stuff. The guy that did it was this guy. It was young Einstein. In fact, he was 17 when he started to think about what it was like to travel at the velocity of light. It's the young people that you're teaching who are building the basis for doing the great work in the future, okay? Darwin, that's the picture we have of Darwin. He really started on this search for what was going on that led to this fantastic book. He was 24 years old. Clerk Maxwell arguably made the greatest contribution of the 19th century of any kind whatsoever with Maxwell's equations. Every time you use a mobile phone, you prove that those equations are a fact. Not what people think, it's just a theory. That works. If those equations didn't work, your mobile phone doesn't work. And when it doesn't work, it's because the battery is gone down. All right? But he was wee Jamie with a little quiff on the top of his head, okay? Young Scotsman. Rosalind Franklin took the greatest and most important photograph of all time that led to the structure of DNA. And Chandrasekhar was a young man when he realized that a star 1.5 times the size of the sun would collapse into a neutron star. And he was not believed. It was such an impossible thing to accept. So that's the thing. They have to realize it's young people, the people you've seen earlier today, who do it. And guys like me are way past it. The next issue we have to address is the language of science.
If you're interested in the ultimate character of the physical world, the complete world, and at the present time, our only way to understand that is through a mathematical type of reasoning, then I don't think a person can fully appreciate, or in fact can appreciate much of these particular aspects of the world, the great depth and character of the universality of the laws, the relationships of things, without an understanding of mathematics. I think it's just, I don't know any other way to do it. We don't know any other way to describe it accurately and well, or to see the interrelationships without it. So I don't think a person who hasn't developed some mathematical sense is capable of fully appreciating this aspect of the world. Don't misunderstand me. There are many, many aspects of the world that mathematics is unnecessary for, such as love, and which are very delightful and wonderful to appreciate and to feel awed and mysterious about. And I don't mean to say that the only thing in the world is physics, but you were talking about physics, and if that's what you're talking about, then to not know mathematics is a severe limitation in understanding the world.
If you get a chance to see the whole of that film, it's made by a friend of mine, Chris Sykes. It's the most fantastic program of any kind, in my opinion, but certainly on science. Now, let's discuss this, because a big problem is the fact that he said that mathematics is required. Well, let's look at my favorite book of the last year, okay? It's called Pi. And this is in Japanese, okay, as it happens, but it's pi to 1 million decimal places. On the first page, it's pi to 100 along the top, okay? And then it goes down, and it goes down to 4,000. That's only 4,000. That's on the first page, it goes to 10,000. Then you have to go through, and I'm going 10 at a time, okay? I'm leaving out every one of them, okay? Well, I've made a film of this. We've not edited up yet. Until we get to the last page, And at the bottom of the last page, that is pi to 1 million decimal places. Now we're talking about billions of pounds, okay? We've got people not paying their taxes, okay, as we know from yesterday. You have to go through this book several times to realize that there are only 1 million numbers, only 1 million on that page. And I think that's the first thing I want to tell you, is to get the kids to realize how big 1 million is, and then realize that 1 trillion is 1 million of those books, all right? And the US national debt is $15 trillion, okay? And some kids appreciate mathematics, okay? Let me show you this one. It says there's the Dirac Equation and the Hamiltonian. Oh, there's somewhat, they've left out a minus sign there, okay. Maxwell's Equation, DNA, Heisenberg uncertainty principle. That was LSD, just in case you wanted to synthesize it. But my favorite is this, and just read what she says. Nicole, a physics graduate student who we've actually met, believe it or not, by sheer coincidence, I saw this particular tattoo, my favorite, walk past me in Lindau last year. And what she says, I consider it the most beautiful thing I have ever learned. That is what a teacher has to do in your subject. Can you get a kid to say that? That's the challenge. And here I am leaning up against a tree at Florida State University and aspects of science. The first is a body of evidence-based knowledge, okay, which you teach at school. The application of that knowledge, technology, and the way that new knowledge is obtained, scientific method, okay? Those are 3 aspects. However, there's something more important. And really, the fact that science is so useful and has become so useful in the last 200 years, we've completely lost the fact that it's a discipline, an intellectual activity, and a culture, and most important, cultural activity. Before it was useful, it had another name. It was called natural philosophy. The most important aspect, as far as I am concerned, by far, is the fact that natural philosophy is the only philosophical construct we have determined, okay, or devised to determine truth with any degree of reliability. I'm going to read it again, because this is the most important thing that I'm going to say, and I'm prepared to argue it out. Natural philosophy, and I'll define natural philosophy, is the only philosophical construct we have devised to determine truth with any degree of reliability. And therefore, the ethical purpose of education must involve the teaching of young people how they can decide what they're being told is actually true. The teaching of a skeptical, evidence-based assessment of all claims without exception is therefore an intellectual integrity issue. Without evidence, anything goes. Think about it. Okay, there are 3 senses. The first one is common sense, okay? Now, common sense tells me that the sun goes around the earth. Who agrees with me? One, thinking about it. I don't know what it does, but in Florida it starts over here and it goes over there. Common sense tells us the sun goes round the earth. It's uncommon sense that was needed to say that it's basically the earth turning on its axis, which makes it seem as though the sun is going round us. The uncommon sense and bravery of 3 people in particular, and Giordano Bruno was burnt to death for this, because people assumed that common sense was that the sun goes round, and they decided he was wrong, and they burnt him to death. Galileo was threatened with the Inquisition. That's only 500 years ago. Most people have accepted the claim. How many of you know the evidence? Okay, this is very interesting, because you've accepted the claim, although common sense tells us the sun goes round, without actually knowing the evidence. What else have you accepted without knowing and checking the evidence? See, I'm not here to make you feel comfortable. I want you to make you think about these issues, because they're incredible. This is an incredibly serious issue today, because most people accept claims for which there's no evidence at all. And this will probably be the Achilles heel of the human race, in the brain of the human race. The trouble is that nonsense is common now, and I'll show you an example. It's in Kentucky. The students of Cincinnati University asked me to come and talk to them, and they asked, and Margaret said he ought to go to the Creation Museum. He blathers about it often enough. $27 million. School kids in busloads go to this, and other groups as well. Did humans live with dinosaurs? I'll let you read it, okay? They lived at the same time as Adam and Eve, and so dinosaurs people lived at the same time. Therefore, we must have ridden them, obviously. What did they originally eat? Before Adam sinned, all animals, including dinosaurs, were vegetarian. Okay, well, you don't need those teeth to eat a lettuce, okay? All right. What happened to the dinosaurs? Didn't get into Noah's Ark. They were drowned in Noah's flood 4,350 years ago. Okay, and Noah's Ark is there, and Noah's there, and he's Scot. He says he's got a Scottish accent anyway. He says, there's a big flood coming, and we've got to build a big boat. Now, the point I'm showing is that children in school are being taught by science teachers who believe this in the United States. I've met them. It's interesting, so I'll think about it. And here's a little girl scratching her head. Science is very, very young. Basically, Abelard in the 12th century in his book, Sic et Non, said, by doubting we come to inquire, and by inquiry we arrive at the truth. Okay? It's a short and profound sentence which encompasses science. And doubt and questioning are an intrinsic threat to those who depend on dogma for their authority. And Abelard got into a lot of hot water, as some of you might know. Francis Bacon in the 16th century wrote a book, Novum Organum, on science. And look what it was called, New Instrument. Science was a new instrument and it did not exist prior to 16th century. Common sense occurred, there was empirical studies, but science did not exist because the language was not there. If we take Pierres Rule and then invert it, what we get is arguably the most profound statement of all time. To determine the truth, we must doubt and inquire, okay, which has explosive consequences. Only where natural philosophy has triumphed over dogma-based authority have democracy and science actually been achieved. Look around at the countries and you'll see that it's only in those countries that we have democracy and science. Well, what is the language? Diophantus had equations. I haven't got time to go into it. But this guy is a Welshman, and believe it or not, in this book, the first book on algebra in the English language, he invented the equal sign, okay? And there it is. The first equal sign was 1550, and basically that was an equation, 14x plus 15. And here we see the rules of subtraction. 10 minus 4 goes to 6, 12 minus 8. That is 1550. All right, so that's Robert Record. All right. Tycho Brahe was the start of science when he made accurate measurements of the motions of the planets. And look at the exquisite beauty of this instrument, okay? Just look at that. You can only say that today you don't even see instruments as beautiful as that. But what he did was get accurate measurements of the planets. Kepler came along. Tycho Brahe died. Kepler then produced his own log tables to do these calculations. Through this massive calculations, he came up with this observation, that basically the orbit of Mars is an ellipse with the sun at one focus. That was the start, an accurate measurement and how to explain it. Newton, as you know, invented integration, but it had already been invented by Archimedes, and differentiation, and that led to an understanding of the motions. The interesting thing is that Newton did not know a half mv squared. So Newton, the brightest bloke we've ever had, did not understand kinetic energy. And I think as teachers, we should realize that it didn't grow on trees. It was, basically, it didn't fall off a tree either. Okay. It was Leibniz who claimed it was mv squared. It was Wilhelm Gravesande who actually showed that by dropping balls into mud, showed that the depth it went down went as the velocity squared. And that was a major breakthrough. Christian Huygens was involved. And now let's look at the simplest of laws, what I call an equation of physics. Lectures on Spring by Robert Hooke. He says that the power of any spring is in the same proportion with the tension thereof. That is, one power stretch it or bend it 1, 2 will bend it 2, and so on. So now the theory is very short, the way of trying is very easy. So we take our band, we put a weight on, it goes down 1. We put 2 on, we go down 3. We put 3 on, we go down 3. We predict that when we put this down, it will go down to 4. Hooke's law is an equation of physics. It's not, there are equations, Diophantus, but we have now an equation of science in which the parameters relate to observable quantities. All right? There's one other thing we need. All right? We need basically calculus. We need to be able to integrate that and we then get basically a half kx squared. We get the energy of the harmonic oscillator with a fundamental oscillator, which is possibly the oscillator of the carbon dioxide vibration. All right? You can't integrate a sentence. You can't differentiate a sentence, and that's the problem, okay? So that was 1550, and Leibniz and Newton were the people who actually achieved that. Now let's get to education, because that's what this is about. I do kids' workshops all over the world. I've done them with the BA meeting for 10 years, about 10 a week. I've done them in Japan, in Santa Barbara, in Mexico, in Malaysia. I've done it by internet to Iceland, to 2,000 kids on the internet across the whole of Australia and the UK. When I show this, sometimes there are screams by young women, but it's not me on the right, it's the bloke with the hair on the left that they're screaming at. This Diego Farlan helped me a fantastic guy, to teach kids algebra of 6, 7, 8 years old. And here, my favorite guy, the only person who's found a use for C60 so far. All right. Now, some years ago, I set up the Vega Science Trust, okay? And we have discussion programs, lectures, snapshots. I want to draw your attention to the snapshots, because these cost £17,500 for 15 minutes. They were shown on the BBC. They're careers programs. They're a fantastic set. I'm very proud of them. And interviews, reflections, science workshops, and basically this. And here they are on biochemists. All, okay, I know that, don't want to. Oh, all right, okay. There must be a way of killing this. Okay, there you go. We've got scientific discussions. Vega, we pioneered a new concept in TV debate that basically participants should actually understand something. Okay. We've got the workshops, fantastic programs by Feynman, 4 1.5 hours, filmed in Auckland. We deal with issues like malaria. In fact, to point out that about 1 million children a year die of malaria because DDT has not been used, because of the embargo. It's interesting. A decision is responsible for 1 million deaths a year. John Cornforth, close friend, who is the one genius, well, maybe one of the 2 or 3 geniuses I know. This guy was at Sussex, and he still lives, he's 95, lives in Lewis. Joe Rotblat, the greatest man I ever knew personally. I've interviewed him on our website, the Vega website, and Max Perutz, who got the first molecular machine, which we talked a little bit about. But things changed. What changed was the encyclopedia. How many of you have looked at an encyclopedia? Okay, this week. Aha. Okay, this is what you were faced with, but not anymore, because what we have now is the GUU wiki world, okay? All right, GYWW, okay? If you look at Encyclopedia Britannica, you see this drawing, not very imaginative. You go to the Google image browser, put any of those things in, you'll get pages and 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 pages, and you'll even get rotating buckyballs. This is a revolution in access to information, triple revolution, okay? Finding it, seeking, accessing it. YouTube, creating it. The kids can make their own programs. And I think the greatest contribution to education is Wikipedia, because 500,000 people altruistically are putting their passion, giving it up to you, to our children, for nothing. And Jimmy Wales deserves everything. I think it's a fantastic breakthrough. We're doing something which is the next step, okay? It's a global cache of information. I'm going to show you what it is. It's GeoSet, and you have the technology here. It's Echo 360, but we have basically this. We have dual window presentations, and I don't really need to be here. I could be in a little box, and you're watching. You'll see the sort of PowerPoint come up like this, and it'll soon be downloadable. We use this sort of situation, and basically it's called GeoSet, okay? Now, let me show you what the students can do. This is just wonderful, basically. Okay.
Here are the Beatles. George, John, Ringo, and Paul. We all know their music, and most of us even know of their impact on the world today. However, whether we realize it or not, we've had more contact with another type of beetle, and they have had far more influence on our very lives. I'm talking about these beetles, the insects. And this presentation will be all about the wonderful world of beetles. So why talk about bugs? They seem so insignificant and so unimportant. Well, first of all, the study of insects is an extensive branch in modern biological research. And for those chemically minded with us, there's plenty of interesting chemistry that goes on inside beetles. But the most important part of this presentation is to show you that beetles are actually very interesting creatures.
I'm going to stop it there because that's an undergraduate. And I get all my undergraduates to make a short presentation about 5 to 8 minutes on the project. Instead of reading a project and having to read this whole thing through, I just watch them on this, and we just put them in the little studio. Graduate student.
Hi, my name is Kerry Gilmore, and I am a graduate student here at Florida State University. I work for Dr. Albugan as an organic chemist. Now, I love organic chemistry because it provides the opportunity to go through and be an architect, an engineer, a builder. You can go through and we can really look at designing molecules. We can figure out how to actually make these molecules, and then finally, we actually get to go into the lab and actually build these things. Now, the greatest organic chemist by far is nature. Nature can go through and take something as utterly simplistic as these small seeds, and through a series of organic transformations using chemistry that we ourselves use, it's able to go through and transform it into these beautifully complex and beautiful flowers that you can see here. Now, what we do is much the same. We'll take something relatively small, something relatively simplistic, and through a series of transformations, we need to figure out how to make something that's much larger, much more complex.
I'm going to jump on.
That you see now on the left-hand side are used as what's called molecular wires or nanowires. And these are very, very good at going through and conducting electricity.
Now then, that's an undergraduate. I thought I'd show you now something by my colleague Steve Aqua, who came with me from Sussex to Florida to help me with my research program. But he turns out to be brilliant, not only helping me with my research, but also in making programs.
Disguise. I had a meeting with Agent X, and he gave me a secret document. There we are. Top secret. Now, the problem is, he gave me all this information. X, right before he disappeared, gave me these two envelopes, A and B. Now, according to him, it contains a secret message. That's a secret message written in invisible ink. Okay. Well, luckily, he told me that he wrote the instructions down and put them in envelope B. And unfortunately, that also says to be written in invisible ink. Never mind though, we can work this out with a bit of chemistry. So, what will you need for today's experiments? Well, firstly, you'll need some kind of heat source. I'll be using a heat gun, which looks somewhat similar to a hairdryer. But anyway, you'll also need...
I'll just jump on. And the thing about it is that in education, you need to put the kids into an environment in which they can experiment themselves, okay? Something that they can do that you didn't think of. And Steve is just great at this, and he's working with us on our GeoSet program. Now, the thing about this program is that we now have done something which I just never foresaw. We've revolutionized the resume. Instead of a pile, if you have a CV, you go in there, we put our kids on top of the file, and you can see who they actually are. And here is the evidence, basically this. Kerry, who you've just been, got a Fulbright scholarship, Okay, Steve put together a beautiful little presentation on our GeoSet program, and we got a Rich Media Education Award. Prajna Adar, the first student that I recorded, got 4 tenure track offers, and they told her at one of the places that we could see from the internet that you can teach. Within 2 to 5 years, you will not be getting a postdoc in another country or a lectureship or a job in a school unless you're on the internet showing that you can teach. There'll be pros and cons, but I think it's inevitable. Our kids are on top of the pile. Brittany said the GeoSet was the defining factor in getting into medical school. Jeff said it was real fun doing it. I think it helped me get my position. Artrees was one of my students. She made a presentation. It was in the reference, as we sent it in the reference for the scholarship. When she got there for interview, they said, we've already seen it. It was great. Okay, she'd already got the job without the interview. This is the future. This is what we should be recognizing is going to happen. There are now companies that require their employees to make presentations on YouTube. Okay, I haven't shown you a fantastic one by Jennifer. She just got into vet school. Dan got the top, this is Goldwater Scholarship is the top award in science for undergraduates. There were only 2 at Florida State. He got one of them. We have a Japanese node that Noriyuka got a job at NHK, the Japanese company, and this is the most interesting. Saino was a postdoc in Toyo University, one of our GeoSet nodes, one of the partners in this GeoSet program, and she sent the URL of her presentation because she wanted a job at Mahatma Gandhi, and she got the assistant professor. She just went recently back to India. And here's an interesting one. My colleague Mark Riley, who's a Brit actually, unfortunately supports Manchester United. I'm from Bolton, so it's a bit of a bad scene for me at the moment. But anyway, nevertheless, he sent these URLs, and the NSF funding people were impressed. You can use these in your reports. You get your best students to do the work for you. So there's no brain. I know that many of you have seen your teachers, so you must have seen this on a Sunday morning. It makes you think, doesn't it? Well, it's a marking. And here I am in my home in England, in Lewis, and I'm actually marking my students who are back at Florida State in Tallahassee because they've recorded their presentation, their projects. I don't get them to write. I now get them to do project presentations. There's some tricks of the trade that I'm using here, and if you want to know what I'm doing, there's a lecture on what I'm doing on GeoSet. Steve Aqua, Sam is a TA. I think he wants to be on Baywatch, actually, from that particular picture, and Colin and Penny, other people. I'm going to end up with what I think is important, and that is to unlock, as I said, the creative potential of every student, okay? And I don't usually show other people's cartoons, but I want to show you my favorite. Schultz is and was a genius, and I want to show you this. C. Sally got a C. A C. I got C on my coat hanger sculpture. How could anyone get C in coat hanger sculpture? May I ask a question? Was I judged on the piece of sculpture itself? If so, is it not true that time alone can judge a work of art? Or was I judged on my talent? If so, is it right that I be judged on part of my life over which I have no control? This is interesting stuff for teachers, right? Because there's a lot of truth. It's funny, but it's true, all right? If I was judged on my effort, then I was judged unfairly, for I tried as hard as I could, all right? Was I judged on what I have learned about this project? If so, then were not you, my teacher, also being judged on your ability to transmit your knowledge to me? Are you willing to share in my C? Perhaps I was being judged on the quality of the coat hanger itself, out of which my creation was made. Now, is this also not unfair? Am I to be judged by the quality of the coat hangers that are used by the dry cleaning establishment that returns our garment? Is that not the responsibility of my parents? Should they not share in my C? The squeaky wheel gets the grease. Now, I used to show this, but now I have an incredible reason for showing you. Because what Sally says and asks is the following, okay? How could anyone get C in coat hanger sculpture? I'm now going to show you. Because 2 years ago, we went, as we always do, to this place. You know where it is? It's the Royal Academy Summer Exhibition, 2010. There was this bloody idiot rabbit on the outside, I don't know why. I don't like it. It doesn't look much like a rabbit or a hare anyway. But there was a coat hanger sculpture in there. Look at that. Well, but that's only a bit of it. Just look at the head. Look. In nanospace. But what about outer space? The third man. There are some bands called the diffuse interstellar bands. They've been seen since 1919. They're nearly 100 years ago. They are not known. There are something now. There used to be 50 to 100. There are now 400 of these. Not a single one of these lines has been identified. They're all over the space. They have puzzled spectroscopists and astronomers certainly since 1936. And certainly, I don't know anyone in my field of optical spectroscopy, which is what I used to do, and astronomy, who would do anything to identify these lines. Wherever you look at any star, you'll see these absorption patterns. We suggested a few years ago that basically C60 could be responsible, a charge transfer band, okay? Basically, sodium plus will stick to C60, and then an absorption as the electron transfers from C60 to sodium, and the plus charge proves to this, the possibility of a charge transfer band. Now, I always thought of C60 as the third man. There's diamond and there's graphite, known to the ancients, okay, thousands of years ago, okay, they've known it. And it just really is surprising that we found it by total accident in 1985, at the end of the 20th century, that the third molecular form took so long to discover. And I thought it was like the third man. For instance, we discovered it in simulating the conditions in a carbon star where all the carbon in your body was formed. The triple alpha process squeezes 3 alpha particles into carbon. 3 times 4 is 12. Another 4 go in, it's oxygen 16. And that's a funny process as well. But anyway, so I thought of it as the third man. Now, how many know of the film The Third Man? Der dritte Mann. Okay. I'm going to show you a bit of it. Okay.
What kind of a spy do you think you are, Satchelfoot? What are you tailing me for? Cat got your tongue? Come on out. Come out, whoever you are. Step out in the light and let's have a look at it. Who's your boss?
Was wollte denn überhaupt ein? Sind Sie deppert? Ja, Sie meine ich, sind nicht so blöd. Eine Frechheit ist das nicht, mit der Nacht so eine Krawall zu machen.
Harry!
Eine Frechheit ist das, so eine Krawall zu machen.
I'm going to stop it there because you can see the rest on YouTube. Okay, yeah, a lot of it anyway. And that's somehow it is fascinating. Here's the third form of carbon, the third man. In the film, people think they've seen it, disappears, and C60 is the same sort of thing. And then I thought, well, it must be somewhere, but I never really realized that it would be so easy to detect it. Whoops, sorry about that. That hyperlink. This telescope, a couple of years ago, came up with a spectrum. And here is the infrared spectrum, emission spectrum, okay? And you see these peaks here, all right? That's the white, is the spectrum of the star. The infrared spectrum of C60 is the red, okay? The infrared spectrum of C70 is the blue. To a chemist, and certainly to me, this is just unbelievable. Here's a star which actually has hydrogen in it, and it's pumping out stuff, and the only thing that you can detect in the fingerprint region is C60 and C70. And the fingerprint region has been used, you know, for 100 years as the way of proving you got a particular group in organic chemistry. And yet, it shows we don't understand the chemistry of carbon, even to this day. It's just incredible. Anyway, that's what seems to be coming out of a star like this. Stars that produce the carbon in your body. So it looks as though some of the carbon in your body was once C60, which is rather nice. Okay, so I'm your godfather. Okay, there you go. But anyway, that's the situation, and I think I'll just show you a little bit. There was a film made in 1992 by the BBC, and this is Wolfgang Kretschmer, a friend of mine, great piece, beautiful piece of science. They just pipped us at the post. Sorry, we nearly, another 2 weeks earlier, we'd have got that paper. We'd have got paper number 1 and number 2. We got number 3. They did a brilliant. It would have been unfair if we'd beaten them, but it was unfair to us too. Anyway, to cut a long story, and as Jeff is here, it reminds me that we were turned down to do the Kretschmer-Hoffman experiment, weren't we?
Indeed.
Indeed, we were. We were turned down by BP, Shell, and the Royal Society. However, that's the way of the world. Anyway, in this film, I'm going to show you the ending. I believe it is there. And it would be rather nice to feel that, in fact, we were on the right track. There are some interesting features in space. And C60 certainly can fit them better than any other proposal that has been made up to now. I'm a believer, and I think ultimately we'll find this there.
But others have said that C60 is nothing like a match for the diffusion stellar band.
They're wrong. Okay, thank you.